What does it mean when reality refuses to stay inside the lines we drew for it? For most of human history, the night sky looked calm, a patient dome of lights, a place for navigation, prayer, and wonder. But the deeper we learned to look, the less peaceful it became. Behind the visible stars, beyond the soft glow of familiar constellations, the universe revealed a character far stranger than our early stories allowed. It is not only vast, it is unruly. It contains objects so dense, so violent, so elusive that even the language of physics begins to tremble around them. We like to imagine science as a steady lantern, moving outward through darkness. And often it is. It names things, measures them, finds order where there once seemed to be chaos. But every so often, discovery does something more unsettling. It does not answer the question. It sharpens it. It shows us a universe that behaves correctly by its own rules, while still feeling impossible by ours. This journey begins there at the border between confidence and humility. In the places where equations still work, but only just. In the moments when astronomers, physicists, and patient observers have found something that seemed, at first glance, too extreme to be real. A star that should not hold itself together, a silence in space too large to ignore. A force shaping the cosmos while remaining almost completely unseen. These are not stories about monsters hiding in the dark. They are stories about human beings meeting the limits of understanding and continuing anyway. About instruments listening to whispers from billions of years away. About minds trying to describe a cosmos that is older, colder, and more imaginative than we expected. And maybe that is the deeper revelation. The universe is not obligated to feel reasonable to us. It only has to be true. The question is whether we are willing to keep looking when truth becomes stranger than certainty. What if a dead star could still reach across the galaxy and touch Earth? In late December of 2004, our planet felt a disturbance from the far side of the Milky Way. Not a collision, not a visible blaze in the sky, just a sudden pulse of energy, brief as a breath, arriving after a journey of nearly 50,000 years. For a fraction of a second, Earth's upper atmosphere reacted to something born around a collapsed star in Sagittarius. A star that had already died and yet still possessed a kind of violence that seemed almost excessive, even by cosmic standards. That object was a magnetar. A magnetar begins as the remnant of a massive star after the star's outer layers have been blown away and its core has fallen inward. What remains is tiny by stellar standards, but unimaginably compact. And in rare cases, it carries a magnetic field so intense that ordinary comparison starts to fail. This is not just a stronger version of Earth's magnetism. It is an environment so extreme that atoms themselves would behave differently inside it. Matter, light, and even the crust of the star are pushed into conditions our laboratories cannot reproduce. Astronomers think these objects may form when a newborn neutron star spins rapidly and churns with extraordinary internal motion, amplifying its magnetic field to astonishing strength. But the full story remains unfinished. We can model pieces of it. We can observe the outbursts. We can watch the aftermath of what are sometimes called starquakes, when the rigid outer shell breaks under magnetic stress. Still, the scale of the power involved feels almost mythic. And that may be the unsettling beauty of magnetars. They remind us that death in the universe is not always quiet. Sometimes collapse creates not silence, but a deeper and stranger form of intensity. A final act so fierce that even across the width of a galaxy, the echo still arrives. What happens when matter is squeezed so far that even language begins to fail? In 1967, in a field outside Cambridge, a young researcher named Jocelyn Bell Burnell noticed a rhythm buried in the noise. The signal arrived with such perfect regularity that, for a brief moment, it seemed almost artificial, as if the sky itself were sending coded messages. But the truth was more astonishing than any joke about visitors from another world. She had helped uncover one of the strangest objects in existence, a neutron star. A neutron star is what can remain after a massive star has exhausted its fuel and collapsed under its own weight. Not into a black hole, not yet, but into something balanced on the thinnest physical margin imaginable. It holds more mass than our sun inside a sphere scarcely wider than a city. The numbers are familiar to scientists by now, yet they still sound unreal. A spoonful of this material would outweigh mountains, Gravity at its surface is so fierce that ordinary intuition has no place there. And still, these stars spin. Some rotate with breathtaking speed, sweeping beams of radiation across space like lighthouse beams crossing a dark coast. To us, those beams appear as pulses, precise and patient, sometimes hundreds of times each second. Inside them, the story grows even stranger. Physicists suspect their interiors may contain superfluids, exotic particles, or states of matter that cannot be recreated on Earth. The equations offer possibilities, but no settled portrait. We know they exist. We do not fully know what they are. That may be why neutron stars feel so haunting. They are not merely dense remnants of stellar death. They are thresholds, places where matter endures just before surrendering to something even deeper and darker. They remind us that nature does not always choose clean categories. Sometimes it chooses the narrow ledge between them. And standing there looking up, we are left with a quiet question. How much of reality remains hidden simply because the universe can become more extreme than the human mind was ever built to expect? Can something be almost invisible and still outweigh entire galaxies? At first, the mystery appeared as a small embarrassment in the math. Astronomers measured the motion of stars and found that the numbers did not add up. Galaxies were spinning too fast. Clusters of galaxies were holding together too tightly. Light itself, bent by gravity as it crossed the cosmos, traced the outline of mass that no telescope could actually see. Again and again, the visible universe seemed to be standing on an unseen foundation. We gave that foundation a name: dark matter. The phrase sounds dramatic, but the idea is strangely modest. It does not claim monsters or hidden civilizations. It simply admits that most of the matter shaping the universe may not interact with light in the way ordinary matter does. It does not shine. It does not reflect. It barely seems to notice the familiar world at all, except through gravity. And yet without it, much of the large-scale structure of the cosmos makes less sense. The evidence comes not from a single spectacular image, but from a patient accumulation of clues. Spiral galaxies rotate as though wrapped in massive halos. Colliding galaxy clusters reveal mismatches between visible gas and gravitational pull. Computer models of cosmic evolution work far better when this invisible ingredient is included. Still, the central truth remains almost paradoxical. Something appears to be everywhere, and we still do not know exactly what it is. That uncertainty has opened many doors. Some physicists search for undiscovered particles. Others explore whether gravity itself may behave differently on enormous scales. The debate is serious, careful, and unfinished. Dark matter is not a solved riddle dressed as mystery. It is a living question held together by strong evidence and incomplete understanding. Perhaps that is why it feels so deeply human. We are surrounded by effects whose causes we only partly grasp. We infer the unseen from what it leaves behind. In that sense, dark matter is more than an astrophysical puzzle. It is a reminder that absence is not emptiness, and that some of the most important forces in our lives and in the universe are known first by the shape of what they move. What if the brightest thing in the universe was powered by something we can never directly see? In the middle of the 20th century, radio telescopes began picking up signals from points in the sky that seemed absurdly powerful and impossibly distant. They looked at first like stars, but stars do not behave that way. They do not pour out such staggering energy from such small regions of space. As astronomers studied them more closely, the illusion gave way to a deeper truth. These were quasars, ancient beacons from the young universe, blazing across billions of light years. A quasar is not a star at all. It is the brilliant heart of a galaxy whose central black hole is actively feeding. Gas, dust, and shattered matter spiral inward, forming a disk heated to extraordinary temperatures. Before that material disappears beyond the event horizon, it radiates with such intensity that the galactic core can outshine all the stars around it combined. It is a strange image to hold in the mind, darkness itself becoming the engine of light. For a time, quasars seemed almost too extreme to accept. Their energy output challenged intuition. Their great distances meant we were seeing them as they existed when the universe was much younger, less settled, more crowded with raw material. And that raised another mystery. How did black holes grow so massive so quickly? How did the early cosmos build such enormous structures in what feels, cosmically speaking, like so little time? Even now, the answer is still being refined. Quasars are not merely spectacular objects. They are archives of an earlier age. Their light has been traveling toward us since before Earth was old in its current form, carrying hints about how galaxies formed, how matter gathered, and how violence and creation have always lived close together in the cosmic story. There is something almost poetic in that. The universe can hide its deepest gravity inside an object we cannot see, yet allow the falling matter around it to announce its presence across space and time. Maybe that is the lesson quasars offer. Not everything reveals itself directly. Sometimes the invisible is known by the radiance it draws from everything that comes too close. What if the universe wrote a mirror image of the black hole and then chose never to show it to us? White holes live in that strange territory where mathematics is clear and nature is silent. They emerge from the same equations of general relativity that gave us black holes long before telescopes could confirm them. If a black hole is a region from which nothing can escape, a white hole is its reversal, a place from which matter and light can emerge, but into which nothing can enter. Not dust, not radiation, not even a stray beam of light. In theory, space-time allows it. That is what makes white holes so unsettling. They are not fantasy added to physics from the outside. They are already there, folded into the structure of Einstein's equations. The puzzle is not why someone imagined them. The puzzle is why the universe appears to permit the idea so elegantly and yet offers no clear example we can point to and say, there it is. If such an object existed, it would look like a cosmic one-way gate. Energy would pour outward. Matter would be expelled with no path back in. Some theorists have wondered whether white holes might appear at the end of a black hole's life, after time scales so vast they make human history feel microscopic. Others have suggested that certain unexplained bursts of high-energy radiation may hint at something similar, though no case has come close to consensus. So white holes remain suspended between proof and possibility. They sit in physics like an unfinished sentence, and maybe that is why they matter. They remind us that understanding is not only about what we observe, it is also about what our best theories allow, even when the sky refuses to cooperate. Sometimes knowledge arrives not as a confirmed object, but as an open door in the architecture of reality, waiting to teach us whether the universe is stranger in practice than it already is on paper. How do you describe a star that seems to survive by breaking the rules that should destroy it? Somewhere in the catalog of the sky, there are stars so large, so luminous, that their very existence feels provisional. According to older models of stellar physics, there should be a limit to how much light a star can produce before its own radiation pushes its outer layers away. Beyond that threshold, the star ought to tear itself apart, shedding mass until balance is restored. And yet the universe, as usual, has provided exceptions that look less like mistakes and more like reminders that nature is rarely finished with our first draft. Among the most striking examples are the giant blue stars and unstable hypergiants found in regions of intense star formation. These are not quiet bodies drifting through space. They burn with extraordinary power, losing mass in violent winds, erupting, swelling, contracting, and in some cases living lives so turbulent that astronomers are still debating how they formed and how long they can endure. Some may be the products of stellar mergers, where two stars combine into one, larger and more unstable whole. Others may survive only because rotation, composition, and internal structure they allow a more delicate balance than earlier theories assumed. What makes these stars so compelling is not simply their scale, it is the tension they embody. They exist on the edge of self-destruction, where gravity pulls inward while radiation strains to blow the star apart. Every observation feels like a glimpse of a temporary compromise, a cosmic negotiation that cannot last forever. Eventually, many of these stars will collapse, explode, or transform into something even stranger. But for now, they shine. And perhaps that is the deeper resonance of these impossible stars. They are not symbols of perfection. They are symbols of instability held in form, of endurance under impossible pressure. They suggest that the universe does not always prefer the simple or the tidy. Sometimes it creates things that survive not because they are safe, but because they have found, for a little while, a way to remain whole at the edge of ruin. What if the emptiest places in the universe were telling a story as profound as the brightest stars? When we picture the cosmos, we imagine abundance, rivers of galaxies, fields of stars, clouds of gas lit from within. We think of matter gathering, colliding, building the visible architecture of creation. But the universe is also shaped by absence. Between the glittering structures we celebrate, there are immense regions where almost nothing appears to be there at all. These are the cosmic voids, expanses so large and so underfilled that they challenge our instinct to think of emptiness as passive. A void is not simply a gap between galaxies. It can span hundreds of millions of light years, containing far fewer galaxies than expected, as though matter itself chose to step aside. They emerge gradually from surveys mapping the large-scale structure of the universe, where clusters and filaments appeared like a vast web, and in between them lay these haunting cavities. The more carefully astronomers traced the cosmos, the clearer it became that emptiness was not a leftover detail. It was part of the design. That raises difficult questions. How do such enormous underdense regions form? Are they natural consequences of tiny fluctuations in the early universe, stretched over time by gravity and expansion? Could they help explain certain anomalies in cosmic background measurements or the motion of galaxies? Most researchers see them as expected features of structure formation, yet some voids feel so unusually large or so suggestively placed that they continue to invite debate, not because they overturn physics, but because they reveal how much subtlety lives inside it. There is something deeply moving about that. The universe is not only composed of what gathers, it is also composed of what does not. The missing, the sparse, the almost silent. In human life, we often treat absence as loss alone, but the cosmos offers another possibility. Emptiness can shape reality just as powerfully as presence. And so the void becomes more than a region of space. It becomes a kind of mirror. A reminder that meaning is not always found in what shines, but sometimes in what the light leaves behind. What if the oldest light in the universe carried a bruise no one can fully explain? Long before stars, before planets, before anything with a name or memory, the universe was a hot, dense fog of particles and light. When that fog finally thinned, the light was released and began its long journey outward. We still see it today as the cosmic microwave background, a faint afterglow spread across the entire skyline. To cosmologists, it's more than radiation. It is a record of the early universe, a delicate map of tiny temperature variations that would one day become galaxies, clusters, and everything familiar. And yet, inside that ancient pattern, there is a stain. It is called the cold spot, a region of the microwave background measurably cooler than the surrounding sky, larger and smoother than many models would comfortably predict. It does not shatter modern cosmology, but it lingers at the edge of it, as though the universe left behind a sentence with one phrase missing. Astronomers first treated it cautiously, as they should. An anomaly is not a revelation until it survives scrutiny, but with better observations, the feature remained. One explanation is grounded and elegant. Perhaps light from the early universe first passed through an enormous underdense region of space, a supervoid, losing a little energy along the way before reaching us. That could help account for part of the signal, but not, it seems, all of it. The shape, scale, and depth of the cold spot have kept the discussion alive. So other possibilities have entered the conversation, more speculative and far less certain. Some have wondered whether it could be the trace of an event from the universe's earliest moments, perhaps even the imprint of a collision with another expanding region of reality during cosmic inflation. Not proof, not consensus, just a possibility that remains difficult to dismiss completely. There is something profoundly moving in that uncertainty. We are reading the oldest light we can detect, trying to understand what it remembers. And even there, at the threshold of beginnings, the universe resists becoming entirely legible. Perhaps that is the lesson of the cold spot. Even the clearest records of creation may carry shadows we are not yet wise enough to name. What if a black hole does not fall silent after impact, but answers back? On September 14, 2015, two detectors on opposite sides of the United States felt a tremor so delicate It was almost nothing at all. In Louisiana and Washington, LIGO recorded a passing ripple in space-time itself, the final vibration from two black holes that had collided more than 1 billion light-years away. It was one of the great scientific moments of our time. Einstein had predicted gravitational waves a century earlier. At last, the universe had allowed us to hear them. The signal was elegant, a rising chirp, then a sudden fade. It matched general relativity with astonishing precision. For many, it felt like closure, a long-awaited confirmation that our best theory of gravity had once again survived the test. But science has a habit of reopening the very doors it appears to close. When some researchers studied the aftermath of that merger more closely, they asked a strange question. What if the signal did not end exactly where we thought it did? What if, after the main event, there were faint repetitions, delayed patterns arriving like echoes in a canyon? In classical relativity, a black hole should not behave that way. The event horizon is not a physical wall. It is a one-way boundary. Gravitational waves should pass inward and vanish from view, not reflect and return. And yet the possibility of echoes has remained in the conversation. If such echoes are real, they may suggest that what we call a black hole is not the whole story. Perhaps near the horizon there exists some quantum structure, a surface or boundary too subtle for ordinary light to reveal, yet capable of leaving fingerprints in gravitational waves. The evidence is contested. Some analyses see hints, others see noise. No consensus has arrived. Still, the question matters, because it points to a place where two great frameworks of modern physics, general relativity and quantum theory, may finally be forced into direct conversation. Black holes have long stood as symbols of finality, regions where information seems to disappear and explanation goes dim. But maybe even there, at the edge of no return, the universe has not finished speaking. Maybe what we took for silence is only a signal we have not yet learned how to hear. What if the universe contains stars made not of ordinary matter, but of something even stranger than neutrons? There are moments in physics when a known object begins to look less like an answer and more like a doorway. Neutron stars are one of those moments. They are already extreme beyond ordinary imagination, compressing more mass than the sun into a sphere the size of a city. But deep inside such an object, where pressure rises beyond anything we can reproduce on Earth, some physicists suspect neutrons themselves may no longer remain intact. Their constituent quarks could begin to roam freely, creating an exotic state known as quark matter. If that happens, then somewhere in the cosmos there may exist quark stars. These hypothetical objects would resemble neutron stars in some ways, yet differ in crucial details. They might be smaller, denser, and stranger in their internal behavior. Their surfaces, cooling patterns, or spin rates could reveal clues that point beyond ordinary neutron matter. A few observed compact objects have tempted researchers into asking whether they are seeing such a thing already, though none has produced a final, widely accepted verdict. The problem is not a lack of imagination. It is that the boundary between an unusual neutron star and a true quark star is incredibly difficult to define from far away. That ambiguity is part of the fascination. We are trying to infer the state of matter into a collapsed star from the faint signals it sends across space. Flashes of X-rays, subtle variations in mass and radius, the rhythm of rotation, the aftershocks of stellar collisions. Each new measurement narrows the possibilities, but the interior remains hidden, as though the universe is willing to show us the shell while guarding the heart. And perhaps that is fitting. Quark stars, if they exist, would not simply add one more entry to a cosmic inventory. They would mark another threshold where matter abandons a familiar form and becomes something more elemental, more difficult, and more revealing. They would tell us that even after a star dies, nature may keep compressing the question, asking how deep structure really goes before the categories we trust begin to dissolve. What if the universe's missing pieces are not hidden in distant space, but in the equations we still do not know how to finish? By now, the pattern is familiar. Again and again, astronomy presents an object or phenomenon that feels as though it should not exist, at least not in the neat way our earlier understandings suggested. Yet none of these mysteries arrives as chaos. They come with data, with signals, with careful measurements. They do not announce that physics has failed. They suggest something subtler and more profound. Physics is incomplete in the places where reality becomes most extreme. This is where exotic possibilities begin to gather. Primordial black holes, perhaps formed not from dying stars but from density fluctuations in the earliest universe. Boson's stars, hypothetical objects made from particles unlike ordinary matter, held together not by the familiar architecture of atoms but by quantum fields on a cosmic scale. Strange stars, dark stars, and other proposed forms that remain somewhere between elegant speculation and observational challenge. Each one emerges for a reason, not to decorate science fiction, but to solve a real tension in theory, a real silence in the evidence, a real gap in the story. Most of these objects may never be found. Some may turn out to be unnecessary once better explanations arrive. That is part of the discipline. Science does not advance by believing every possibility. It advances by testing them, keeping what survives, and letting the rest fall away. But even the discarded ideas matter. They show us where thought has been forced to stretch. And perhaps that stretch is the point. The universe does not merely offer us facts. It trains our imagination under pressure. It asks whether we can remain rigorous without becoming rigid, curious without becoming careless. There is dignity in that balance. So these hypothetical objects deserve our attention, even in uncertainty, because they reveal the frontier not as a place of answers, but as a place of disciplined wonder. And maybe the real mystery is not that the cosmos contains things that seem impossible. Maybe it is that the human mind, brief and local as it is, can still sense where impossibility ends and deeper understanding begins. What do all these impossible objects have in common, beyond their scale, their violence, or their mystery? At first, they seem unrelated. A magnetar cracking under the pressure of its own field. A quasar blazing around an invisible abyss. A void so empty it changes the map of the cosmos. A cold scar in the oldest light. Strange stars, hidden matter, hypothetical remnants born from unfinished equations. Each one appears to belong to a different chapter of physics, a different method, a different era of observation. But if we step back, another pattern begins to emerge. These objects do not simply challenge what we know. They reveal how knowledge grows. Science is often described as the conquest of ignorance, but that is only partly true. More often, it is a conversation with uncertainty. We notice an anomaly. We test the instruments. We doubt the interpretation. We compare, refine, argue, measure again. And sometimes what first looked like an error becomes a doorway into a larger view of reality. The history of astronomy is full of those moments when human beings thought they had reached the edge of explanation, only to discover that the edge was really an invitation. That process is not cold. It is deeply human. Behind every detection lies patience. Behind every theory, imagination disciplined by evidence. Behind every revision of what the universe is, there is also a revision of what we are. Creatures small enough to be humbled, yet stubborn enough to keep asking questions of a sky that owes us nothing. Maybe that is why these cosmic mysteries move us so deeply. They are not only about distant objects, they are about the relationship between the mind and the unknown. About what happens when our need for order meets a reality more complex than our first beliefs. About the grace of admitting that the world is not simpler because we wish it to be. And so, before this journey ends, one thought remains. Perhaps the strangest thing in the universe is not the black hole, the quasar, or the unseen matter between galaxies. Perhaps it is the fragile intelligence on one small planet that can look into the dark, recognize its own limits, and still choose wonder over fear. So where does all of this leave us after the strange stars, the unseen matter, the ancient scars in light, and the objects that seem to stand just beyond the reach of ordinary explanation? Perhaps here, with a quieter, wiser idea of truth, we began with things that appeared not to belong in a sensible universe, objects so extreme they seemed to violate the rules that were meant to describe them. But as the journey unfolded, a deeper pattern came into view. These were not really exceptions to reality. They were reminders that reality is always larger than the models we build to approach it. Physics is not a cage around the universe. It is a language we refine, one discovery at a time, as the cosmos reveals new dialects of matter, energy, space, and time. That realization carries a kind of humility. It tells us that knowledge is not weakened by mystery. In many ways, it is made possible by it. Every unanswered question becomes a reason to listen more carefully. Every anomaly becomes a test of whether we can remain honest enough to say, we do not know yet, and brave enough to continue anyway. There is something deeply human in that posture. Not triumph, not surrender, just attention. And maybe that is why the sky still matters, even in an age of screens, schedules, and noise. When we look outward, we also look inward. We see how small we are, but also how remarkable it is that small beings can ask large questions. We are made of temporary matter on a brief world, and yet we have learned to detect echoes from black hole collisions, to map invisible mass, to read the afterglow of creation itself. That is not a minor achievement. It is one of the great expressions of human curiosity. The universe will keep its distance. Some of its secrets may remain unresolved long after us. But that does not make the search meaningless. It may be the search that gives meaning to the silence. And so the final question is not whether the cosmos is stranger than we imagined. It almost certainly is. The real question is whether we can keep meeting that strangeness with rigor, wonder, and care. Because in the end, the story of the universe is also the story of our willingness to keep learning from what we cannot fully hold.